from time to time with things that I think there are a little bit of a must-watch. And the first one is the computational fluid dynamics lessons by Lorena Barba. For those of you with the open form incentive, there's also a CFD Python 12 steps to Navier-Stokes, which could be of kind of help. But this is a must. I mean, this course is like, I mean, usually, at least in my country, a CFD course is for undergraduates. Is like they have lectures, which they mostly don't attend, and then they use Fluent to do tutorials. And Fluent's tutorials are really simple: push this, push that, do this, do that. That's not how CFD is supposed to be. In this course, they don't even do any post-processing. They just study, I mean, you know, develop the Burger's equation and code it by different discretizations. Very good. Of course, for those of you who still want to, get in touch with software, there's an ANSYS course. There's also a Cornell University free course that you can take. And I really recommend Professor Bad Bloken course. And, you can find it in Coursera. It's a course about sports and building aerodynamics. And what's so interesting in this course is that this professor is simply oozing with enthusiasm to his profession. His phenomenological explanations are wonderful. I took this course, and for the more advanced guys, there's a combustion course, which is really rare, from Professor Heinz Pitch, which is world-renowned in his field. I think those of you who are interested to go on and do combustion is going to get really in the mainstream in the following years. Perform large eddy simulations in combustion, because most of the action is away from the walls. So here's a course. Learning combustion is pretty hard. Then there's from University of Kentucky, the McDonough series. I really recommend, for any one of you, highly recommended reading the lectures on turbulence and turbulence modeling. I mean, he has kind of a point of view of a mathematician, and it's really interesting to get a different point of view of all the pitfalls that statistical approach to deterministic equations like Navier-Stokes puts in front of us. To those of you who are interested in OpenFOAM, I mean, I don't even need to say, Tobias Holzmann just opened his new site, even fixed his book with some turbulence mistakes he had. Then there's the mentorship, which till a week from now, I'll decide if I'll remove it totally, or I don't do it financially. I mean, it's just for so right now it's going pretty good, but it's actually almost free. One more. Is the lectures from McDonough on compressible flow? No. No, he has incompressible flow lectures. But you can, if you want to learn about compressible flow, I would recommend, first of all, you have many books about it, but P.S. are good books, very good. Also about large eddy simulations. And so let's start. Let's start. Let's share a different screen right now. Share. Let's start our. I need this. Yeah. Just disturb me. Okay. So it actually had a different picture, but now that I have my cool logos, I'm going to use them all the time. Two more. Chat. What are the assumptions while solving Navier-Stokes equations? That's a weird question. The assumption is that you are in the continuum, which means that there's what's called the spectral gap between the molecular and the what we call infinitesimal, derivation, and that's the main assumption that we use. The Navier-Stokes equations are emergent equations, what they call emergent equations. I mean, they are deterministic equations, but why am I connecting to the Zoom again? Am I disconnected?
We can hear. No, it's fine.
I see you, but
we can't see the presentation.
Do you see the screen moving, or?
No, we see you meditating.
Is the screen moving right now?
Nope.
No screen.
The shared screen is gone.
Yeah, I know. I don't know why. Oh, I see. The internet stopped working. Okay. Now it's going to be fine. I'm going to reconnect to the Zoom. Okay. Share screen. Okay. Screen is back, right? So I'm not muted. Screen is back?
Yes.
Yes, sir.
Great. So we're gonna start. You are muted. Okay. We're gonna start with a little bit of CFD modeling goals. This is as simple as it gets. Results to be achieved, simplifying assumptions to be made, and whether they are actually can be made. This is very important. Physical models to be included in the exploration of the range of validity. Okay, we have a range of validity. Can someone give an example for a range of validity that is, I don't know, just shoot one example where you know you're out of your range of validity. An example for that is trying to get high resolution flow with Reynolds average Navier-Stokes equations. that could be out of your range of validity. If the model has, you cannot model rotating flow, really rotating flow with simple two-equation models. Regarding the above, retain an expected accuracy considering the statistical measure is achieved. Okay, we're going to see what it means and why. Retain how quickly the results to be achieved. So this means that the last sentence is one that I wanna really put my finger on. We never want to start a project when all we think about is, do we have the computational resources for that? Okay, so and I don't mean, I decided I want to do a DNS to an airplane. I mean simple CFD, Reynolds average, Navier-Stokes. You should be able to do it with almost every geometry. If you find yourself all the time fighting with computational resources, get a better computer. And remember that all of the above interact with each other. I mean, simplifying assumptions to be made and whether they are actually can be made. Okay, if the simplifying assumptions cannot be made, the results will not be achieved. If the physical model to be included in the exploration is not in the range of validity, then you need to use a different physical model, and perhaps then you cannot have enough computational resources. Everything is connected here. A CFD workflow usually works like this. You define the model problem at hand according to CFD modeling goals. You perform a pre-calculation to establish a better understanding of the phenomenology, achieving bounds, a route for exploration. This means that we usually don't go and simulate without thinking before that. I mean, we're kind of, and the vendors are trying to push us also that even the top-notch vendors trying to push us to simulation. It's everything is very easy. Everything is very immediate. No, I mean, if you go to old school CFD practitioners, they used to use a lot of pen and paper before doing calculations. You rarely see today people use correlations or stuff like that. And that could be a problem. Simplifying the model to account for approximations and exclude CFD passive features. Okay, so the first one, sometimes I'm weary about, because sometimes what you think is symmetry could not be right. And furthermore, it could sometimes I mean, it could really cause problems. But do exclude passive features. I mean, you don't need to have, if there's a bolt insert inside a hole, I mean, you don't care about the results there. There's no need to model it. You can't model it. You're just going to get a higher aspect ratio between the full domain and the littlest, the smallest part of your feature. Define a domain to include only physical results. Right. This is very important. You should look at it this way. I mean, you wouldn't like, and there are rules of thumb. We're going to get there. You wouldn't like the numerical boundaries to impact and location where the solution counts. Okay, it can become very important. I mean, in large eddy simulations and stuff like that, because you need to get the right turbulence content. But anyway, if you have, if you're solving a problem, yeah, I see the chat. How would you go about choosing the right turbulence model for a problem that you are tackling for the first time? Oh, that I'm going to answer. You know that turbulence is my. You're going to get the essence of turbulence. I mean, I think after this one, you won't need to think too much about turbulence anymore. You want to understand at least about runs, everything you need to understand. But very important, the numerical domain. If it's aeroacoustics you're doing, you can't have reflections from the walls. If it's if you're solving a problem of an atmospheric boundary layer, you need the atmospheric boundary layer to become an atmospheric boundary layer before it gets to your building. And so you need to take this into account. This means that the domain is usually larger than you want it to be. I think your voice is not clear. Am I right? My voice is not clear? Is my voice not clear?
No, it's clear enough.
It's fine.
Yeah.
Clear now? Okay,
Yep.
I'll hold the mic. No problem. Define mesh resolution according to appropriate features. Okay, computer resources, they do count. Physics, numerical description, turbulence, other physical models, prediction of high gradients, etc. This is, of course, we're going to get more into it in a second. Still CFD workflow, set up the solver. Solver is very important. I mean, select an appropriate physical model, of course. If you need to, if it's fluent, then there's a viscous button. Then you choose whether the flow is laminar, viscid, or kind of turbulence model. If you need combustion inside, radiation, it needs to conform with the physics of the model problem. Define material properties. You need to be usually, as a suggestion, read the guidance of the specific platform. I mean, like in Fluent, you need to have in a mixture of water and air, the water before the air. If you want to get humidity, it's simple stuff that can make you stuck. But of course, definition of material properties is very important. Take into account that there are simplifying assumptions that you can do. I mean, solving a problem with natural convection with the full energy equation is a waste of time. There's the Boussinesq approximation, meaning adding another term to the let's say Z is up to the Z momentum equation, and you should take that into account. Don't go with the 5,000 kilos hammer every time. Prescribe operating and boundary conditions. I'm very sad to notice that many who do CFD don't even know the difference between total pressure and what static pressure means and what dynamic pressure means. But that's one thing. Not all definitions of boundary conditions are the same. I mean, if you need to, you might think I define the mass flow rate in the or a volume flow rate in the inlet, or I can the same way. I know the area. I know then I can define a velocity inlet. It is not the same. I mean, usually most softwares prefer to have conditions like velocity inlet and pressure outlet. So it's important because they transform and to velocity anyway. So take this into account. Prescribe initial conditions or initial values based on educated guess or previous solution. Of course, if you don't have a physical solution, there are many ways to initialize the domain. Besides the boundaries, we need some kind of number in every cell. There are many kinds of initializations, and this could mean that a difference between, it's not only will take more time, this could mean a difference between diverging or converging. Previous solutions, I mean, sometimes you'd like to take scale adaptive simulation and use it as a basis for a large eddy simulation or stuff like that. Set up the solver, density or pressure based and steady or transient. We'll see the difference between density or pressure based solvers. There's not much difference. Usually when you have to use density based solver, you're working with a tough problem. Choosing solution algorithm. Solution algorithm means usually it's supposed to converge, but sometimes solution algorithms are like coupled algorithms or the incompressible simple and the simple family of algorithms. Density-based solvers have also their respective algorithms, and set up spatial discretization according to the level of accuracy to be achieved in tuned solution controller. Okay, there's many ways to control the steps that you make besides choosing the algorithm itself. The under relaxation factors, meaning I take I take a step, but then I take a step back, okay, and I do a little step because I think doing this big step is going to make me diverge. Understand what it means multigrid. You know, these are not things that we are going to deal with here, but you need to understand what I mean. You can read it at McDonald's PDE book. Set up solution monitors, of course, and again, I suggest, and I also provided quite a. I have it in my. You can use it. You can use it for every software. Set registers. Registers means that you register what happens in every cell in every iteration. So if you find yourself diverging, Okay, you diverged, and now everything is a mess. But then you can repeat a simulation, wait for the minute you start to diverge, and look for the problematic area. You can do that by setting registers to certain velocities, or I don't know, whatever you think is messing your solution. Okay, complete solution iteratively solving discretized conversions and conclusions in convention and achieved. That's a little bit. Feature flux balances. Okay. This is important. I mean, especially when you solve energy-related problems with radiation, because radiation is like solving a different problem than the CFD. And you need to check flux balances. I mean, there is no way you don't have, you don't conform the mass balance or the energy balance. Things cannot go away. You need to check this. Okay, so this is not really related to our discussion, but when we have, usually when we use runs, we check for integral quantities like drag or lift, or sometimes mean velocity, first order statistics. But when we use the large eddy simulations, then it's different. I mean, you need to check for higher order statistics in order to know that you're not looking at nonsense. Consider revising the model. Okay. First of all, sometimes checking different ways to model the same thing might be a good idea. Usually in runs, what we do is what is called a mesh independence procedure, which means that we refine the mesh and check for we have some kind of a rule. I mean, 5% of change is good enough for me, and then I can take the solution as the right solution. If you're doing large eddy simulations, this won't work because usually you're already working with most of your resources. So usually when hybrid or large eddy simulation are concerned, what we do is the opposite. We take the mesh, we increase it by a factor of 2, and we just check. Of course, the results are going to be different. They're going to be less accurate, but we check to see if the phenomenology still appears. If it doesn't, it means that we don't have the right resolution. Always try changing. I mean, it's a good idea, but we're going to see how to check if our boundary layer is right, or this and that. But it's good. It's a good thing to replace topologies and check other topologies. I mean, I will give you some examples that will a little bit astound you. Okay, simplification of geometry. First of all, I never recommend reading directly. Yes. Do we have to resolve the problem if we have applied dynamic meshing? Do you have to resolve the problem if you have dynamic meshing? You don't have to resolve the problem. What do you mean, for mesh independence or to check mesh independence? Yeah, I mean, that's the problem you're solving. If I, for example, did a pulsating heart. Yeah, yes, of course you do. Of course you do. Because that's the problem you're solving. If I'm doing a pulsating heart, then the whole mechanism is like the squeezing and expanding of the heart. So there's no way to run away from it. And of course, if it's a dynamic meshing, then maybe your results are correct at one change of the mesh and not in other. I mean, yeah, you should solve the problem like you solve the problem. I mean, I don't see how a dynamic mesh problem cannot be dynamic mesh. Okay, thanks. What I said is never take. Usually, you can read with Fluent or other platforms directly to space claim SolidWorks files or others. Don't do that. It's very problematic. Always ask the designer to. Why am I still hot here? Always ask the designer to. Okay. Always ask the designer to give you an XT file. Okay, it's very important because the way he translates the problem might not be the way that your software translates the problem, and that could cause real issues. I think this is an unsolvable problem for the foreseeable future. How to communicate with the mechanical designers. I mean, they do the design. Sometimes it's good, sometimes it's bad. You see here missing faces, stuff like that. Most of the softwares today, yeah. It doesn't appear. I found Gambit itself to be ideal for cleaning. Yeah, man. I found Gambit itself to be also. I'm with ANSYS before ANSYS bought Fluent, and I'm with Fluent before ANSYS bought Fluent, and but Gambit is not supported anymore, so you can't get any help for problems that you have, and you might find some issues with, roundup errors that it makes. So I don't know. I don't know anyone who uses Gambit today. Do you?
Yeah, I used it. I don't know if you can hear me. But yeah, I'm not great.
You still use Gambit?
Well, it was installed on one of our work computers before it stopped being supported by ANSYS. So we were kind of lucky in that.
Yeah, but it's not supported by ANSYS anymore, and
yeah.
I don't know. Everything you see here is stuff that most platforms got. ANSYS. I think the most brilliant thing ANSYS did in the past 10 years, besides not being stupid and starting developing fluent meshing is buying Space Claim.
Right.
It's amazing what Space Claim can do. Chat. How was time? What's the time?
It's
I don't have a watch.
In your time, it's probably 8:45.
It doesn't matter. Yeah, it's 8:45. Okay, I want to go quick through these. I don't find them. Space Claim, I mean, overpowers them, and so does every other software today. Simplifying geometry became really easy, and also there's a fault tolerance. Every vendor has its own fault tolerance. Rajat, you told me you started to learn the fault tolerance. Yeah, so you get a crappy geometry and then it overcomes it. Fluent mesh workflow. I don't want to talk about fluent mesh in separately. I don't think it's part of the best practice guideline. Okay, what do we care about when we talk about meshing? And then I'm going to stop this presentation for a minute and move to one of my posts. Accuracy, desired mesh quality, maximum skewness. In the case of was actually more in the case of tetras. Now mostly when you use polyhedras, it's the orthogonality that you need to check, because polyhedra is a little bit harder to get skewed. But aspect ratio, usually you have to tolerate it. I mean, in the boundary layer, you'll have a huge aspect ratio sometimes. Efficiency, desired cell count, yes. I think ISM still lacks a lot of Gambit tag to primitive face mesh. What do you mean?
I think I was just responding to someone else what they said. But I remember I was looking for something to do in Gambit.
Yeah, ISM is great, but and Gambit is great, but producing a mesh with fluent meshing or with pointwise, with respect, especially with complex geometries, then to do that same with ISM could be really exhaustive. And one of the expectations from NASA was to take the man out of the loop. I mean, CFD practitioner should only check the post-processing. You shouldn't be messing with structured, hard to define mesh. I mean, some of you, maybe are using ISM so much that they feel like it's the easiest thing to do. Cut here, cut there, cut here, cut there. But it's really not that efficient to work with complex geometries and meshers like mesh generators like Gambit or
I agree.
Hypermesh. I don't like this company. Don't like them. I hate them. I was supposed to get, I was interviewed to get a local manager in Israel, and they told me the job is yours, and I was kind of happy back then. Pointwise is more effective than fluent meshing, right? Pointwise is awesome. I mean, because nothing compares to what they do in pointwise. But fluent meshing is, I don't know about efficiency. I mean, if fluent meshing is really easy to use. They have this workflow now, but the workflow is still very limited. I mean, 5 years ago, when you were working with not with the workflow, you had to have some expert with you to teach you how to do stuff. Because it was really hard. You needed to be an expert to produce a mesh. Then they went to the workflow and it became really easy. But there is a lot of stuff you can do with the workflow, like having different kind of inflations, boundary layers, types, or it's not there. ANSYS decided for some odd reason that what they want to do is make workflow is awesome. Yeah, it's awesome, but it's very limited. I mean, if you decide to go on with smooth transition, then you'll have to do smooth transition everywhere. In the inflation, and that's kind of problematic. You have less control over the stuff that you. Yes. Yes, but then you have other stuff that you have to define, like if you're going to do stair-stepping, or you're going to do this, or you're going to do that. I mean, they made a big mistake. They've decided that the mechanical mesh is going to be the mesh for everything. And the mechanical mesh is horrible for CFD. I mean, it was simply horrible, and so they got retarded for a few years. Yeah, remember that you have to pay for pointwise after a month, I think. Of course, so it's good to start to learn. You have to pay. You have to pay for every software, don't you? Okay, so desired mesh quality. Mesh quality is very important, especially in the boundary layer, but not only in the boundary layer. We'll see some meshes that would astound you that are better for some kind of applications than others. But especially in the boundary layer, we want our inflation, or let's say I call it orthogonal layers. The prism layers that are orthogonal to the gradient of the flow. You want it to be as best as you can, because otherwise you'll get a big truncation error, and it's going to mess up your results. Accuracy, efficiency, desired cell count, low cell count. Low cell count for resolving overall features versus high cell count for greater details. That's of course right. We all know, I don't think there's anyone here who will disagree. CFD resources can always get out of hand, even with Reynolds average knife bestowals. Easiness to generate, faster dominant mesh versus created hex hybrid. That's all the stuff. Mostly they're doing, I think, polyhex core or poly. If when it's better to do polyhex core, and when it's when to do a poly mesh. or when to do a hex mesh. I mean, a hex mesh, which is body fitted, you can only do with ISIN, of course, but it's going to be very hard. Polymesh is very good. You get prism, of course, in the inflation, in the boundary layer, and then you get and then the rest of them is just polyhedral. And then you have polyhex core, which means you have two layers connecting the boundary layer with polyhedras, which are not prism, to the hex core. And the hex core is simply a cut cell. I mean, it doesn't have, it's not body fitted. So if you have like curved flow, you have like swirling flow, then using hex core is not so good, because then you don't get anything from using hex core. It's like using tetra. And when you use polyhedras, you have more chance of having of decreasing the truncation error, because it can set better to right. So we're going to see a specific example for that. Okay, skewness. Everybody knows what skewness is. Skewed cell. We want our skewness to be lower than 0.7 usually in the surface mesh, in order for it to be under 0.9 in the, yeah. Wait. What are you chatting about? What kind of we should consider as good mesh quality and should proceed for? Okay, so I'm going to say it now. For skewness, 0.9, you can continue forward. If it's a dynamic mesh problem, you should be a little bit less, a little bit more conservative, because the dynamic mesh might quickly diminish the quality. So you'd need probably to start with a better, with better than 0.9. I mean, but the same with aspect ratio. Aspect ratio usually doesn't mean too much, because of course you're going to get high aspect ratio inside the boundary layer. It's not so good to have a high aspect ratio. I mean, with like some smoothness in the flow. So having cells inside like a jet with high aspect ratio is doesn't make sense, and it's also not going to happen. You see here hex mesh versus tetrahedral mesh, and what you're supposed to see is that when the flow is aligned with the cell surface, then it makes a difference that you use hex mesh over a tetrahedral mesh. When the flow does not, you see that the results are kind of the same. Okay, so that's why when the flow is curvy and very sophisticated, it turns and revolutes, then you'd rather use polyhedra. I mean, if I had like a helicopter, then usually what I do is use an inner mesh where the flow is really with large rotation, with polyhedra and polyhex core only outside. So I'll split the mesh and connect it, or something like that. But the larger the larger the angle is from the the orientation of the flow to the cell front, then the truncation error is going to be bigger, and that's always like that. This one I've added today. I think many of you don't consider when you. That's what I actually. The difference between defining different methodologies of inflation. I mean, every kind of inflation, besides being able to, if the geometry is very sophisticated, and you need the coordinates to connect with boundary layers and stair stepping, and it's hard, and sometimes you can't use a specific one, then another one. Yeah. No, we're going to talk about numerical diffusion. Rajat. We're going to see numerical diffusion. We're going to see it big time. Yeah. It's not only numerical diffusion, also dispersion. Yeah. So there are different ways to. Of course, you have a few parameters. You play with two, you get the third one. There is entered. There is no if there. I mean, there is no sense to use a uniform mesh if the boundary layer changes enormously. The same could be. You should check the mesh, and we'll see how we check the mesh. But here you can see the difference between the. These are specific to Fluent, but I can invent a million kinds of. I mean, I can go with first cell and growth. I can go with, but each of them are going to give me something else along the flow, and you need to consider that because once you do not cover the boundary layer and or with the right resolution, then your error will be large. Okay. Okay, the difference between pressure-based solvers and density solvers is quite known. Usually we usually use density-based solvers today mostly for problems which are high Mach, very high Mach, and these are problematic problems. Pressure-based solver could be used even till I don't know, Mach 3, I think. You have the segregated solvers, which means the simple kind of solvers, and you have the coupled. Okay. Otherwise, it's quite the same. I mean, the only difference is in the density-based method. You, of course, solve all the species, energy, momentum, mass, everything inside one together, because you have the thermodynamics to solve, and then you go and solve the turbulence equations. Here you first solve the momentum and continuity, solve mass, momentum, but you do also repeat, every iteration back this loop. Okay, so yes. No, I don't recommend using density-based solvers for no reason. Pressure-based solvers are a lot more robust. There is no reason to choose density-based solvers for a problem which doesn't need to do anything specific with the thermodynamics of the flow inside. I mean, in a very high Mach, you could get a phenomenon like the chemistry changing. Okay, so there's no way to not use density-based solvers. But usually we prefer to use pressure-based solver for most of the problems. I don't remember. Okay, pressure-based solver, as I said, you can use them. Traditionally, it was for incompressible flows, but you can use them to 2 to 3 Machs. Density-based solver normally used only for higher Machs numbers and for capturing and interacting shock. But again, writing such a sentence is very funny. I mean, like boundary layer shock interaction is a problem which is not quite solved yet. Pressure-based segregated projection algorithms. You have my posts about projection methods. Simple corrected, piezo, maybe control to stabilize convergence through under relaxation factors. Again, did anyone not understand what under relaxation factor is? It's like taking, I have like to walk from the beginning of the room to the end of the room, and instead of taking 10 steps, every step I take half a step. Okay, I just use little steps, and sometimes this sometimes it helps with, but then it takes a lot more time to converge. Yeah, again, taking in mind that this should in turn decelerate the convergent process. Pressure-based coupled algorithm may be controlled by stabilization of the Courant number. Today, I think the influence specifically, it's using the, how is it called? It's not using the coupled, right? It's using the, never mind. Yeah, but it doesn't have the Courant as a default. It has a time scale. Yeah, but I for a long time I prefer to work with the Courant, but it doesn't matter. I mean, it's the same. It serves the same as the under relaxation factors. Better stabilization of the pressure-based solver can be achieved by pseudo-transient option, of course. This doesn't matter. Pressure-based solver. Okay, now there. It says here couple takes 120 iterations and simple takes. Not really. I mean, sometimes it could be the other way around. Sometimes one cannot converge and the other can. And there is no really saying that simple is slower than coupled. But sure. The density-based solver is applicable when there's strong coupling, I mean, when there's a thermodynamic issue, a hard thermodynamic issue, maybe shock boundary layer interaction or high Mach flow where the chemistry changes, and you need to solve all of this together. There are explicit methods, implicit methods. Everybody knows the difference between explicit and implicit. The density-based solver may be explicit method calculate the state of the system for later time. It's a little bit faster. The difference is that usually explicit solvers are very sensitive to the CFL condition, which is like the size, some kind of measure of the size of the cell and the time it takes the phenomena to pass the cell. And so usually in explicit you'll take smaller time steps, but we're not going to get so inside this, inside the stuff here. Okay, this I was thinking if I should talk about. I think it's a little bit too, but it's important to realize. Here you see the Burger's equation. The Burger's equation is a 1D equation, non-linear. It could be linear. In this case, it's a linear equation. And you see here expanding over U minus 1 and to a Taylor series. Okay, then you get some kind of equation which is called the modified equation. You choose the accuracy, and then you have kind of an effective Reynolds that you. It could present also the Reynolds cell problem. But what I wanted to talk about here is numerical dissipation and numerical dispersion. Usually, the higher the order of the truncation, the higher the order of the discretization we take, the lower the truncation error is, of course. Usually the even order derivatives are the ones who are controlling the numerical dissipation, which means the smearing of the solution, like you saw in the hex mesh when the flow wasn't aligned with the cell. That's a truncation error, which is numerical dissipation. And the odd order derivatives cause numerical dispersion, which is like wiggles in the solution. Most softwares don't use anything, unless they are in-house, then second order discretizations. So you should expect the dispersive and especially the numerical dissipation every time when the flow is not aligned with is not orthogonal to the cell face. Every time, in every location that it happens, this is a location where the truncation error adds up. Okay, that's something that should be known. Here you see it again, effect of discretization. If you have we saw it before. First of order upwind is usually when we usually start the simulation with first order upwind because it's a very dissipative scheme. What's good about it is that it allows us to get an very dissipative scheme, but get closer to the solution. First order upwind will not be tolerated in any publication. I mean, you cannot even offer a publication when you did a CFD with the first order scheme. The second order upwind scheme and the whole idea of upwind is that we get our data from the the upstream. So that's a little. That's what Patankas thought makes more sense. That was his incentive for going for the second order upwind. It has a condition. It has some kind of condition limiter in there, but usually, why is it like that? But usually it doesn't. The quick scheme, as far as I know, does not improve anything to the second order upwind scheme. Only in certain cases where the flow is really aligned with the cell. Same is with the muscle scheme. Yes. The solution is smeared across the surfaces. What does dissipative scheme physically mean? A dissipative scheme means that we cut if it's first order, then we cut the second order from our let's see here. It means that we throw from our Taylor the second derivative. If we throw the second derivative, we said that even derivatives are in charge of dissipation, numerical dissipation, and the R derivatives on the dispersion error, numerical dispersion. Then if we use first order, it means we threw the second order from the Taylor expansion. Then we get a large dissipation error, numerical dissipation. It's like and you see it here. I don't think you see it, but it's like another. You see it here. It's like another object that joins the dissipation. Okay.
I see.
Okay. Time-dependent problems. If we use it's usually as I said before, the characteristics for velocity times delta t, typical size cell. It's usually better described as the time it takes the phenomena to pass that cell. Okay, and in explicit schemes, there is a really harsh current. It's log sensitive to current number. In implicit schemes, it can be unconditionally stable, but if the current number is such that, I mean, the cells are such that the phenomena goes too fast through the cells. I mean, the cells are too not refined enough. You just get a big error. Okay, so you won't get a divergence, but you get an error. Here are some estimations you can get. They actually work. I use them. I use this one for turbo machinery application of like a rotor that you put inside a blood vein, and yes. Smeared across surfaces for explicitness at CFS should be under 1, correct? It depends what you call it should be under 1 for finite difference scheme, where everything is the same size. But usually what it means is that phenomena cannot go faster than the typical cell size. I mean, that's it. So you have some kind of, ways how to choose the delta t for certain, but this is more about, this is less about convergence. It's more about, what you see here is more about estimation of a time step to generic problems. Okay, it's not about current. It has nothing to do with current number. Okay, this is time-dependent problems. Initial conditions critically important, of course. You can run the solution a little bit, until you get a realizable solution, or you can run a steady state before that. We do that with the very known von Karman problem. We run a steady state simulation. Of course, it's dependent upon the frequency, but we still run a steady state problem before that, and then move to transit problem. Avoid using results from diffuse time steps before settling trend to residual receiving. So this is, of course, right. Okay, the number of iterations. Usually, you'd prefer not to make too many iterations inside a time step. You'd rather lower the time step. Okay, understood? I mean, here it says 20. 20 is kind of it's not it's a rule of thumb, but you should not run 100 iterations per time step. If you have this kind of problem, then just lower this lower the time step, and that's what you should do. Reduce time step to achieve better conditions instead of increasing the number. Okay, that's what I just said. For pressure-based solvers, it does not include the radiation, blah, 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 blah. Conversion might highly the Senita algorithm. What it does, it skips some of the steps when some of the parts of the pressure-based solver converges, then it doesn't touches them anymore. It's just you can use that. Don't know. Here is a little bit something that is not related to what we're talking about right now, but usually when we have when we were using Reynolds average Navier-Stokes equation, we wouldn't get more than first order statistics. Okay, but that's what we get. I mean, the mean velocity. We can calculate integral quantities like the integral of the pressure distribution over the wing, but we don't get second order statistics or PSD, or because we don't have any turbulent content. Okay, we're gonna focus on runs here. We're going to focus on runs. When we talk about Reynolds average Navier-Stokes equations, it means we split the velocity to an average velocity and a perturbative velocity. Okay, then we do an ensemble average. Usually, it's called, they say time or ensemble average, but there's noise from someone. There is some noise from someone. Yes, can you hear me?
Yeah, we should.
Yes, so usually yes. Nice. Okay, so we do a decomposition to an average velocity and a perturbative velocity. It's written here time or ensemble average, but if we want to get the UDT, then we obviously must have an ensemble average. An ensemble average means that it's like taking many experiments and then doing an average. Okay, instead of doing a time average. Because if we do a time average, then there is no time in the equation. What we get is the same equations as the Navier-Stokes equations, but we get another term here. What's interesting, I bet no one has told you that this term here actually arrived from the nonlinear term, from the advective term. So it's a little bit weird that we have a stress term. So what this actually means that Reynolds average Navier-Stokes equations are a little bit dissipative. Okay, they take a convective term and they turn it to especially when we invoke the Beginings hypothesis, they turn it into a dissipative term. So this is of course a symmetric tensor. Yes. Can you repeat the ensemble average? What ensemble average is? Ensemble average, it is not time-based. No. It's like taking an experiment and then repeating it over and over and over and over and over and over and getting a result every time and then dividing by the number of times you took the experiment, instead of just making one experiment and then doing a time average of it. Okay? It's very important because otherwise you cannot do. No one has anything? It's not. Okay. Different turbulence models. What you see here is essentially the Beginings hypothesis. the Buzynski hypothesis, the eddy viscosity model. There are eddy viscosity models, there are non-eddy viscosity models. Non-eddy viscosity models is where we don't use the Buzynski hypothesis. The Buzynski hypothesis ties between the Reynolds stress and the gradient of the average flow velocity. Okay, so non-eddy viscosity models are like Reynolds stress models. Okay, it's written here Buzynski approximation, but it's Buzynski hypothesis. Buzynski approximation is a whole different thing. It's what we talked about with the buoyancy. Okay, so there can be what we see here is a linear relationship, a linear eddy viscosity model. It's important. I'm going to show you an example for other eddy viscosity models, which are nonlinear. Okay, modeling of turbulence, Reynolds average. There is actually, we connected here, the eddy viscosity is a feature of the flow, not the feature of the fluid, okay? Instead, unlike the dynamic viscosity, okay? And by dimensional analysis, you just simply have to have a length scale and a time scale, or a length scale and a velocity scale. Here you can look at the choice is length scale and a time scale. It could be the turbulent kinetic energy and its dissipation, or the turbulent kinetic energy and the specific dissipation. It doesn't matter. But if we have two equation models, then we call it closed. Why? Because we don't have to guess any. In the past, they were using mixing length models, one equation models. In each of them, you had to somewhat guess and then calibrate a model per area for some length scale. Here you have two transport equations. Transport equations means you have an advective term, a convective term, a production term, a dissipation term, two PDEs for each of those dimensions you choose, and you can choose whatever you want. One turbulent scale, usually they choose the kinetic energy, which is provided from the solution of the transport equation. The second scale, this is really not, doesn't matter. Invoking the Reynolds decomposition, performing manipulations. What you see here is not the exact kinetic energy, turbulent kinetic energy equations. Okay, we can derive it. It's easy to get the kinetic energy. You just multiply the velocity. I mean, if it's specific energy, then just multiply by a perturbative velocity. But what we do is usually after we do the whole, it's not a turbulence course, but after we do the whole decomposition, we get a lot of terms which are like triple correlations between perturbative velocities. What we want to get is not to have any perturbative velocity in the equation. So here you can see the gradient assumption, different assumptions. Okay, this requires ad hoc assumptions. I mean, this is not an exact equation, and this is very important to note. Okay, how we get the epsilon equation? Usually, we can get the epsilon equation by deriving it from the Navier-Stokes equation, although it's very complex. So what we do actually is simply use an analogy to the kinetic energy equation. We multiply each term by epsilon over k and add a specific empirical constant, because we don't know what the ratio really is. And we get another equation for this time for the epsilon as the dissipation. So that's the derivation of K epsilon model for the same choice. Now, most of you know and use either the K epsilon equation or the K omega equation, right? Now we're going to see the difference between the K epsilon and K omega. The K epsilon has two problems. First of all, the epsilon equation cannot be integrated through the viscous sublayer. What is the viscous sublayer? I have to go for this to here. Share. I'm trying to find. Okay, I did it before, but now I think I still need to do it again. Where is the law of the world? Here it is. Open a new tab. Okay. Here is the law of the wall. Okay. The boundary layer, the turbulent boundary layer, unlike the turbulent boundary layer, unlike the laminar boundary layer, which is parabolic for the case of, let's say, a pipe or channel flow, is comprised of a few different matching zones. These zones are matched by perturbation analysis. You see there is no real match here, but we usually take regards to the viscous sublayer, which is a linear layer, sometimes called also the laminar layer. Okay, this is a logarithmic graph. The y plus is the distance, is a universal distance from the wall. We can, from every y plus, calculate physical y, okay, which means that we need to place the first cell away from the wall in this physical y. But it looks like this. We have the viscous sublayer, we have a connecting layer here, which we don't regard. It's called the buffer layer. And then there is the log layer. What you can see is that, as I said, the epsilon equation cannot be integrated to the wall. It cannot get a Dirichlet boundary condition, which means that it needs to, if we have to, if we have some calculation which needs, which the physics effects are important, like drag or like thermal issues, we need to use some kind of wall treatment. That's why you'd always see in the K epsilon many wall treatments. We're going to see them afterwards. And the inertial range we see starts at y plus 30, but it doesn't end. It doesn't have a defined ending. The larger the Reynolds number is, the larger the ending of the log layer is. But we still have to maintain the right resolution, okay? So if we have a low Reynolds, maybe the logarithm, the inertial sublayer or the log layer ends at y plus equals 400. So can you hear me? Yeah. So it's very important to note it's fast. It's crucially actually. Okay. So best practice for EVMs. Let's go back to the screen sharing. I'm not quite done with that. I want you to understand exactly what is the difference between the models you use. Okay? So the epsilon has its problem. It cannot be integrated to the wall. It needs wall treatment. Wall treatment means either we use wall functions. We have some types of wall functions, but this means we have we don't have a non-slip condition. We use some kind of velocity away from the wall, okay? Or we use what's called the low Reynolds model, which in the past was it's still based on the Van Driest damping functions. And the problem with them is that they're nonlinear and stiff. So it's not an ideal model. It's called the wall sensitive model. This model, the most known model, and it's the most important model, and I still think it's the most important model by Jones and Launder at 1972, was derived. After that, Wilcox took and derived the K omega model. But the K omega model, which Wilcox derived, had it could be integrated all the way through the wall. It was not wall sensitive; it was wall insensitive. But it had a strong dependency on the free stream values from the inlet. Okay, it means that little changes in the inlet could make 20% difference in the eddy viscosity calculated in the omega, but eventually in the eddy viscosity calculated. To alleviate this shortcoming, what Menta did in 1992, while on NASA, it was not in ANSYS yet, he took the K epsilon near wall behavior. He took actually both of the models and joined them together, but solving only a K omega model, meaning he transformed the K epsilon to a K omega. Okay, it's really easy. You can take a substantial derivative here and get omega from epsilon. Okay, so what he got instead of the K omega of Wilcox, he got another term here, which is kind of a cross diffusion term, which most of the time doesn't do anything, but it has a tremendous effect near the end of the boundary layer. So by that, he solved the problem of the omega being very sensitive to free stream values. But the other problem that the K epsilon has is it was found to not delay separation. I mean, separation was found delayed whenever you use the K epsilon model, and this remained here. There is no difference. I mean, it remained here. So for that, in the same year, it's actually the same publication when he derived the BSL model. He also derived the shear stress model. The shear stress model is based on, if we look on any two-equation model, we have this connection between this relation between the shear and the production of kinetic energy and its dissipation. Usually it's 1. But when there's an adverse pressure gradient, a pressure gradient, a negative pressure gradient, then it's bigger than 1. And when it's bigger than 1, we get no separation or delayed separation, sometimes even no separation. What he proposed is using the Bradshaw hypothesis. And by that, he simply solved the problem of, he claimed to have solved the problem of delayed separation. But essentially, the publication of Menta was about aerodynamic flows. Aerodynamic flows of the regular type. And sometimes you can see that this A1 here, it is too rough in the case of the SST. So it really does work better for aerodynamic flows. That was the name of the publication, but it could be not better than the, I don't know, realizable K epsilon or the BSL for the other cases. And you can change this A1. So that's the difference between the 3 models we have. Turbulence models, we have Spalato-Maras. The Spalato-Maras model was tailored fixed for aerodynamic flows, external aerodynamic flows. It's really tailored. Each term was tailored to perform very well. It's very efficient in flows around wings and stuff like that. The standard K epsilon is a model for high Reynolds. It's a high Reynolds model. Of course, we talked about the fact that it's all the K epsilon model are wall sensitive. The standard K omega is not used except for cases where there is no free stream. The boundary layer connects between the 2 sides. And then there's the BSL, which is not written here, but it exists. It could be used. Sometimes it's even better than the SST. Here you see it's the ANSYS recommendation to use the realizable K epsilon, which uses realizability conditions for extreme variance in the shear. And then there's the Reynolds stress model, which is not an eddy viscosity model, meaning it's not dependent on the eddy viscosity. We simply calculate the Reynolds stresses. The problem with this, with the RSM, is that it's very stiff. It has many coupled unknowns. The numerical solution. The advantage it has is that, as you ask hypothesis, we get a connection between the shear stress. It's exactly like when you calculate the shear stress at the wall. You say tau equals minus mu t times du dy, right? So, but actually, the part of the stress here, the gradient of velocity that we get here, is the symmetric part of the shear is the symmetric part of the velocity gradient tensor, and the antisymmetric part is the rotation. So that's what we do get. But again, usually it's not worth it. What is a new model that is used today now in Fluent is called the explicit algebraic Reynolds stress model, which actually uses a non-linear eddy viscosity assumption, and such. And as such, it actually takes into account stuff like rotation. Okay, now we're done with this. Let's do a new share. This we saw. Okay, here you can see how the truncation error actually works. You can see how this delta y here. If you get tetra, you can never get the flow aligned with the tetra, because tetra changes orientation all the time, and truncation error is what's the interesting thing. Okay, now rule of thumb is have at least 15 layers inside the boundary layer. Okay, at least 15. Sometimes in cases like where they have to have very low margins, they use even 40 layers. It's very important. But the way to check the boundary layer, covering all the boundary layer, is using the eddy viscosity ratio. It's very important. Not the velocity. I mean, the velocity could lead you astray. It could look like you cover the boundary layer, but you don't. The eddy viscosity is maximum around the middle of the boundary layer. Yeah. What do you mean only isotropic component? Isotropic component of what? Oh, okay. I'm not sure I understood, but okay. Topology of mesh. Topology of mesh is very important. This is something very interesting. What you see here is a cubic lid-driven cavity problem. If someone doesn't understand, it's a cube. The upper face is moving with a certain velocity, and we'd expect that this cubic lead driven cavity problem would be tailor-made for hex mesh, right? Because it's a cube. But as it appears, because of the recirculation areas, polyhedra mesh performs better than hex mesh in this case. So sometimes things like that should be taken into account. Okay, the last part I want to talk about the mostly important for those of you who do verification process is solving the equations right. Verification is the process of determining that the model implementation accurately represents the developer's conceptual description of the model to substitute the model. Or simply put, solving the equation pose the problem. If you don't code the equation, they're sufficiently accurate. That shouldn't pose a problem. But one issue with verification could be, again, the fact that you can't get grid convergence. So maybe you're using low order to low order of discretization scheme, but in most softwares we use second order upwind, so there's no problem with that. The issue of grid convergence, you can see here one that I did for a certain problem. It's simply taking and refining the mesh and getting kind of band. A few considerations of particular importance to EVMs. EVMs, I mean, additive viscosity model. The choice of turbulence model may impact the effectiveness of the procedure. For example, it is incorrect to refine a high Reynolds wall-sensitive model such as the K epsilon. I mean, you want to do a grid convergence for the K epsilon model, standard K epsilon. You cannot do that because you cannot enter the viscous sublayer. That. Generally speaking, the most straightforward. If flows are concerned, it is most important to assess the impact of the mesh refinement in locations of high variance. Okay. I mean, where the flow doesn't change, so that's okay. We always should remember this procedure of grid convergence, which means that we have verified the equations. A verification procedure is necessary, but it is not sufficient. Of course, if you didn't solve the right physical model or problem, then although grid convergence, that didn't describe the right phenomenon. Here comes the invalidation. Validation is solving the right equation. Okay, solving the equations right that you can get by grid convergence. Here it's solving the right equations. The formal definition of validation, meaning the degree of which a model is an accurate, meaning invalid model that represents the physics. Okay, we usually do this how? By experiment. There is a process. Yes, it's very easy to say that I got a different. It's not so easy to conduct an experiment that validates CFD. Okay, measurements are very hard. They are measuring devices have their own accuracy. You cannot put them. They interrupt the flow. It's not always that is documented. It's very hard to validate CFD by an experiment. It's not as easy as it seems. My voice is breaking. Okay. That's another thing. Let's be realistic. Due to the knowledge gap, time overhead, limited resources, conducting validation experiments is rarely done. Okay, measuring a temperature over a component is not a validation of a simulation. Okay, that's enough for me. Here you see a problem which is very interesting, where EVMs fail totally because of the inability to account for rotation. What happens is that the flow actually that's the Stanford diffuser. It actually shows something different. Look how it's supposed to be, and it actually flips it. That EVM model actually flips it. It's so wrong that it's horrible. Okay, near wall behavior, we've talked about it. Standard wall functions, scalable wall functions is the option that, in the case of Fluence, it's 11.1125, I don't know, but scalable wall function exists in every vendor. It means that it decides whether either you're in the log layer or you're in the viscous sublayer. Non-equilibrium wall functions for cases where we have jets or impingement. Low Reynolds models, they are problematic. Okay, I think that's it for this. Now let's look a little bit about on-meshing. with some meshing metrics. The difference between structured meshing and unstructured meshing should be, I mean, ISIN is not structured meshing, okay? Structured meshing means that you can take every point from the physical domain and throw it inside like a cube-like computational domain, solve the problem here, and transfer it here. Unstructured mesh is easier to build, but and when the complexity of the geometry is very high, then there's no other choice. Convergence time, of course, if you can do a structured mesh, is a lot more efficient. Tet versus poly, we've talked about before. Okay, here you see again the issue of hex mesh when the flow is aligned, and when the flow in trim and tetra mesh. You see that because the flow is not aligned with the faces, you have the truncation error, the numerical diffusion, and the numerical dispersion, of course, and other. But when the flow is not aligned with the cell face, then it looks quite the same. Okay, so there's no real difference. Fully automated workflow versus practitioner control improved algorithm meshing. What do you prefer? Do you prefer the role? And someone said the workflow is awesome. Maybe one day we'll have like a fully automated mesh, verified and optimized. And I mean, that's the, I think that in the very near future, with machine learning, and it's going to happen. The man in the loop, nonetheless, that most people simulate but don't really understand phenomenology and not the CFD itself. I mean, what the turbulence model means, what the phenomenology means. Simply some buttons and they push it in. It happens a lot. I'm kind of ashamed to say that I get confronted with people that I would be CFD lab professors at colleges in my country. And they even fix of CFD bit. Yes. Someone has any question? Can you hear me? Am I talking to myself? Okay. Why do you keep asking in the chat? You can talk. You can talk, my friends. Audio breaking sounds like a poor connection. Okay. Any specific questions that you have before we move here? Okay, higher order methods. I think they're going to enter. Some software already use them. One of them is this one, LCS Fast. Most of you know it, I hope so. This is a Q&A kind of thing. Why are second order upwind so dominating today? Well, some of this goes to inertia. There has been so much effort in the past decades to advance robustness and efficiency of second order numerical models that it seems optimal for most applications. But it doesn't mean that we could not gain a lot of knowledge by using higher order models, especially as we saw, the numerical dissipation and numerical dispersion, which could be much reduced. Higher order models, higher order discretization also don't have to be more expensive, because you can then use larger mesh. I mean, you don't have to have the mesh as refined. Okay. There is a thing with which is now very hot, which is age adaptation versus P adaptation. I mean, adapting the mesh, age adaptation, you all know, is like taking the mesh and refining it, okay? And P adaptation is a different kind of adaptations, is taking the polynomial and raising it, okay? To go to a higher order discretization. And play between the two should is something that is really working on. Nonetheless, that when we are talking about large eddy simulations and especially DNS, higher order methods are becoming quite essential, because especially at the area between the subgrid scale, the SGS and the resolved scale, and exactly where the filter cuts, over there we get large errors because of non-commutative operations that we do. Okay, so we're kind of through with the it's already 11 past the time we should be done. So any questions? Specific questions? Maybe about maybe I didn't cover some kind of issue. Yes. Again, I'm not sure I understood the question. A square cross section. A square. Yeah. So. Yeah. So when you have a square cross section, I mean, what you're going to have is like recirculation areas in the corners. Yes. So I mean, I'm not going to tell you what to try exactly, but over there the explicit algebraic, and I'm going to show you also now specifically something very interesting, which is here. Okay. First of all, the option of the, I don't know which software do you use? Which software? Okay, so first of all, you have the explicit algebraic Reynolds stress model, which in application containing rectangular corners like a rectangular channel, exactly what you asked. The Buzynski hypothesis would not do, the linear one would not do, and here you see the exact problem you were talking about, okay? This is a DNS, okay? Oh, you can see that page. Okay, because I didn't share it. I'm stupid. Stupid me. Share. Now you can see, right? Exactly. Okay, so as I said before, when we are talking about the Buzynski hypothesis, we have this du dx, we have the shear, but we are not, we are taking out of the Reynolds stresses what is the rotation, which is the antisymmetric part of the velocity gradient tensor. That's a problem exactly in those cases you were talking about. Here you see a square duct, okay? Here you see a DNS, a direct numerical simulation. Of course, it's correct. Assume that. Here you see what a linear stress-strain relationship would do, which means absolutely bullshit. And here you see a nonlinear stress-strain relation. You can see the secondary flows. It's maybe on DNS-like, but you can still see the secondary flows. It's even not turbulent content. It's still, we're still talking about Reynolds average Navier-Stokes, okay? But with a nonlinear stress-strain term, okay? So you have this in Gecko, but you also have this in the EARSM, okay? The EARSM, the explicit algebraic Reynolds stress model, which is, you can also use an RSM model, but the EARSM is advantageous in the fact that it's not as stiff, okay? It's stiffness is a problem, which means that numerical stiffness may cause divergence very quickly. It's very hard to because of that, to solve problems with Reynolds stress models. So either use the EARSM, or you can use a nonlinear stress-strain relationship in Gecko. You have this option. No. Curvature correction? No. The curvature correction would do for cases like when here. This is what the curvature correction would do. Okay, that's exactly what the curvature correction would do. It will give you better result in a U-turn, but it will never give you. The reason is that the stresses cannot are too strong. They penetrate in the linear stress-strain relationship. The stresses penetrate too strongly to the corners. That's why you don't get its recirculation thing. Okay? That's the issue that you have. The simple fact that the stress penetrates the corner. It doesn't allow for this to happen. So no, you cannot use the curvature correction is actually based on the same curvature correction which is in Spalart-Almaraz model. It's the Schur-Spalart curvature correction, and it's kind of, we have like nothing, anything more than that. The problem with the Gecko model that they didn't give and they will not give any numbers for it. So right now you can mostly use it, either you explore it by yourself or you can use it either as a K epsilon realizable or as a K omega SSD. And you can add stuff like, what you see here, but then, I mean, it's not really there yet. Any other questions? Mm-hmm. Okay. Here you see some kind of example where we said the K epsilon delays separation. In this case, it doesn't even give a separation. Okay, you see that the SSD model shows clear separation. In the K epsilon, it doesn't exist at all. So that's one of the problems that the K epsilon has. Here, on the other side, it is shown that it's actually a non-axisymmetric jet flow using the K epsilon model. Actually, it was found that for specific jet flows, the K epsilon gives better results than the K omega SSD. Why? Because okay. Any other questions regarding solvers, regarding discretizations, regarding turbulence models? Any questions regarding LES or something else?
Yeah, I have, hello everyone. Yeah, so I have the question, I think it's a very basic question about what's the difference between LES and runs.
Oh, in Reynolds average Navier-Stokes, what you do is you decompose the flow to an average velocity and a perturbative velocity. And you actually model all the turbulence. All the turbulence is modeled. What you do in LES is you resolve the mesh until some ideally to the Kolmogorov scale, then you'll have a direct numerical simulation. But because you don't have this kind of computer resources, then you actually put a low pass filter on the equations, okay? So then you have resolved scales, okay, resolved scales until you get to some level where there is a subgrid scale, which is a model also. And the funniest thing is that when we talk about two equation models, we say they are closed, right? Remember, they are closed because we don't need to guess anything. Do we have two equations, two transport equations? LES is not closed because you have to guess the size of the filter. You have to decide where to put the filter. Okay? So, but the difference is that in LES, we model some of the turbulence, which is resolved by the mesh, and we assume that the model that we cannot resolve is representing the dissipation till the Kolmogorov scale. But every large ID simulation kind has different properties. Some of them actually large ID simulation is even older and deeper in theory than Reynolds average Navier-Stokes. Large eddy simulation they started working on large eddy simulation in the 50s and runs only opened in the 70s with the Imperial College of London and Johnson Launder. So that's the difference between large eddy simulation and Reynolds average and Navier-Stokes equations. And it's a huge difference because it means that in large eddy simulation you have turbulent content until some level, of course, but you have turbulent content. In Reynolds average Navier-Stokes, you don't have any turbulent content. All the turbulent content is inside the model. That's a big difference. But as Spalart said and assumed, we wouldn't be able. The problem with large eddy simulation is the near wall area. When we use large eddy simulation, the area near the wall where we have solid boundaries is probably 95% of the mesh. So we can't really solve a lot of problems wall-bounded less. That's why I said in the beginning that combustion, which actually the flame is away from the wall, is gaining a lot of adaptive wind because of the option to explore the turbulence contents of the kinetics inside the flame. As Pollard said, we wouldn't be able to do a complete airplane with large eddy simulation at least until 2017. We have other methods which are called hybrid methods, which means that some of them are like detached eddy simulation, where we switch between Reynolds average Navier-Stokes near the wall, and then large eddy simulation all over away from the wall. But they have their own problems because connecting runs without any turbulent content and large eddy simulation with turbulent content is proved to be, that's what's called the gray area. It's proved to be very problematic. What is gaining a little bit wind is what's called WM-less. which means that you put a small layer of Reynolds average Navier-Stokes near the wall and on all the zones without dependency of the mesh at all, and you do large eddy simulation everywhere else. But again, hybrid methods kind of suffer from, there are two kinds of them. One of them is the zonal method, where we decide a priori where the last zone is going to be and where the run zone is going to be. And one of them is the monolithic, like the detached eddy simulation. When we get to a level of mesh which is refined enough, it switches to large eddy simulation, and then back to, when it's not refined enough, it switches back to Reynolds average Navier-Stokes in one equation, like the Spalato-Maras equation, or the K-omega equation, in the case of Fluent. But they suffer from a lot of problems. That's why you see, if someone of you read my detached eddy simulation, there is a detached eddy simulation, shielded detached eddy simulation, improved shielded detached eddy simulation, and it still goes on, but still unresolved. Still unresolved because the problem of transferring, especially transferring from runs to large eddy simulation. I mean, you don't have any turbulent content. You model all the turbulence, and then suddenly you need to have some turbulent content inside the large eddy simulation zone. One way to overcome this is using the scale adaptive simulation model. If you heard of it. Have you heard of it?
Yeah, is it the mesh adaptive or another thing?
The scale adaptive simulation model, I have here, scale adaptive understanding second generation neurons each one. Okay. It works. It work? Yeah. Okay. Scale resolving simulations and blah 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 blah. Neurons less scale adaptive simulation. What it does is simply it uses it's a kind of formulation that uses the some kind of approach which allows not for eddies not to unite in a specific shear layer width. Okay, what does happen always with runs. Okay. It always goes to the width of the shear layer, and then you get some turbulent content. You see it here, so it can be used as it was offered as a way to use it for the transfer of from runs to less in hybrid simulations. To tell you the truth, I think this method is bullshit. It depends on the von Karman length scale, which does this which prevents from the eddies to reunite till the size of the shear layer. But I don't think it means anything. I mean, there is no proof that the content that is shown here, I mean, is something that is either like larger simulation or something like that. And again, okay, there's here you see there's another method called puns where you what you do is you partially average the Navier-Stokes equation, and for both of them there is suggestions to use them in what's called zonal hybrid runs less. I mean, you have a zone which is runs, you have a zone which is less, and then perhaps if you use one of these methods, either the partially average Navier-Stokes or the scale adaptive simulation, you can transfer some turbulent content to the large eddy simulation area. But it's we're still not there. Still not there. And the near wall area has demands like for large eddy simulation, like DNS almost. You can stretch the cells, you need to get to the Kolmogorov scales, and it's not possible. Okay, I think we're going to, if you don't have any other questions. Someone? Okay, so thank you very much. It's not so obvious that you took the time to join me here. My next time is going to be spent more on large eddy simulation and a little bit hybrid simulations because of the complexity of these topics. I suggest, I mean, thinking about joining. Thank you very much for joining, and
thank you very much. Bye. Have a nice night.